Yeah, training. Okay, so how do you train a neural network? If you still remember gradient descent, it's that. You're using gradient descent for neural networks. Of course, you could see some terms here that we have not used before, such as forward prop. So basically, you're just doing this whole computation here. That's forward prop. I'll show examples later. And then you get the loss. That's what we do in gradient descent, and then get the gradients. That's backprop. That's the term that we use. So, and then what else? You update the weights with the gradients, and then you iterate until you've achieved the maximum number of epochs or iterations for the stopping criterion. The loss hasn't changed after X iterations. So it's really gradient descent, to put it simply. What else? Testing, you just do the forward prop. That's it. So let's go back again. Let's do forward propagation. Just let the numbers flow. You basically compute for this function here by plugging in the inputs that we have. That's it. So for example, you have these skip. You don't really care. Then you get 0.73, then that's your output. That is forward propagation. It's as simple as that. Okay. So what's important to us is to compute the weights, because you already have your input, and then you already know the output, because this is a supervised machine learning problem, right? Now, what you want to get are the weights, very similar to linear regression, implicit regression. So yada. Let's just compute for the weights. Yeah, let's do the whole thing again. Then you end up with 0.73. So how are we gonna get the weights? So we do back propagation. So we get the gradients basically, and then let it propagate backwards. So you start with 0.73 here. What's the derivative of this? It's simply 1. And then what's the, oh, sorry, this is just a simple cheat sheet. So it's easier for you guys to validate later on if you really want to check. But for the purposes of this class, let's not compute each of those manually because it's going to take time. I'm just going to show you that what you're doing is just propagating the error backwards. So you start with 1. Now, what's the derivative of the previous node? So it's basically this, the top derivative times the local derivative. So 0.53 times 1 is, sorry, negative 0.53 times 1 is negative 0.53. So that's going to be your derivative here. And then if you're computing for the derivative of the previous node, you're going to get the derivative of the succeeding node and then multiply it to the derivative for that particular node. So it just goes backwards. That's why it's called backpropagation or backprop. So negative 0.53 times e raised to negative 1. This is the output. Then, yeah, backprop. You get the idea. So it's just moving backwards up until we're computing for the gradients of all the weights that we need. But in order to do that, we have to basically compute for everything, every node. It's for us to get the gradient for, say, for example, the W sub 0, you have to compute for the succeeding nodes. You have to compute the gradients of all of them. That is why it's called backpropagation. We start with this one first, and then we go backwards up until we compute for all of them. So the ending is we now have the gradients for the weights, for all of the weights that we have. That's what we need. And then we do forward propagation now with these gradients taken into consideration, because once you have these gradients, you will now subtracted, right, to the original value of the weight. So you keep on doing that up until it converges. Yeah, this is the sigmoid activation function. It's this. Blah, 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 blah. Still following so far? Sorry, the sequence got messed up. But yeah, so if you still remember, this is the logistic regression equation. You only have one layer here. Now you have two layers. So this is what's happening. See, this is for the first layer, and then this one is for the second layer. Or 3 or 4, up to you. There's no limit. You just add more layers. And you keep on doing this. And the computational graph representation of this one is this. This is the bias. Okay, 3-layer network forward propagation. So if you want to implement the forward propagation part, it is this simple, actually. So we compute for the, let's just use Z1 variable for the pre-activation function implementation. So you basically just do the matrix multiplication and then add the bias. So the Z1 for the first layer. This is for the first layer, second layer, third layer. So we have computed for Z1 now that is now an input for A1. A1 is simply the output of your activation function, and one of the input for that is the, and if we go back to the equation here, where is that? Yeah, so it's Z, right? The sigmoid here, that's the activation function, and put a Z, basically all the nodes before that. So you're now applying the sigmoid function to the output of Z. And yeah, you just keep on doing that. Now the input for Z2 is the output of this one, the previous layer, A1. So that's why you see A1 dot dot. This is just a matrix multiplication here, and then W2. So just keep on doing that. You can have like 4, 5, 6 layers. You do the same thing. And same goes for the backpropagation, the derivative. Yeah, as I mentioned, if you add a fourth layer, it's gonna be that. Yeah. If there's a fourth layer, it's going to be like that. Still following? There's no need for you to implement this, by the way. This is what's happening behind the scenes. Just showing you. Although this is an oversimplification of that, this is the vanilla case of neural networks. We have so many architectures in neural networks. This is the most basic example. Yep. This is backpropagation, so you see it moving backwards now. So we compute the gradients of all the weights.